All right, here are the examples that we've got for the reteach. I just want to make sure that you've got answers to them. So in example 1, we have a ball thrown straight up into the air. That's an important piece of information with an initial speed of 50 meters per second. So if we're looking at the information that we have now, the ball is thrown straight up into the air. That tells me right away that my acceleration is 10 meters per second squared, and that acceleration is down, and that the initial velocity is up because it's thrown straight into the air, right? So that initial velocity is going to be up. It happens to be 50 meters per second, so the acceleration is going to be negative. Now, for this problem, because it's thrown straight up into the air, it's just a y problem. So both of these things are y direction stuff. So starting out, this is the information that's going to be true for the whole problem. When we are specifically looking at the maximum height of the ball, again, the acceleration in the y direction, because this is all a y problem, is going to be 10 meters per second squared down, and we're going to make it negative because we throw the ball straight up. So the initial velocity is 50 meters per second up, and then maximum height. One hidden piece of information we have at the maximum height is that the final velocity is 0, and we're looking for a delta y. So with these 4 pieces of information, the equation that we use is v final squared is equal to v initial squared plus 2a delta y. We're going to put our numbers in. So 0 squared is equal to 50 squared plus 2 times negative 10 times delta y. And we're solving for delta y. So as we move things over, we're going to subtract 50 squared from both sides. So we have, that goes away. 50 squared is equal to, negative 50 squared is equal to negative 20 times delta y. And if we want to find delta y, we're going to divide both sides by negative 20. Those negative signs go away, the 20 goes away, and we get delta y is equal to 50 squared over 20. So if we want to put that into our calculator, we can pull our calculator over here, and we can say, right, we've got 50 squared divided by 20, giving me a delta y of 125 meters. All right, that's one way to do an object thrown straight up. We have more examples of that. So for our next one, we've got how long does it take for the ball to reach its maximum height? So we're still at the maximum height. We still have our acceleration in the y as negative 10 meters per second squared because we throw the object straight up. We still have the initial velocity as 50 meters per second. We're at the maximum height, so we know the final velocity has to be 0. And the question is looking for time here. So the equation that has all 4 of these things in it is v final equals v initial plus acceleration times time. And again, because it's the straight up and down, we're only looking at the y problem stuff. So we're going to plug in our numbers. 0 is equal to 50 plus negative 10 times time. So we're going to subtract 50 over on both sides. That 50 goes away. We get negative 50 is equal to negative 10t. If we're going to solve for t, we're going to divide both sides by negative 10. And so t comes out to be negative 50 divided by negative 10, or 5 seconds. That's how we do that part of the problem. And again, this is still the same problem down here. So how long does it take to return to its initial position? We're still at how long, but now we're looking at initial position. If we go up and then right back down to the initial position, it tells me that my delta y is 0. That's that extra piece of information I get there. So for my knowns, again, the acceleration in the y direction is still negative 10 meters per second squared. My initial velocity, because we threw it straight up, is 50 meters per second. We're going to the initial position, so my extra piece of hidden known information is that my delta y is 0 meters. And we're looking for time yet again. So this is a little different from what we did before. Right, the equation that has all of those things in it is the third equation, delta y equals v initial times time plus 1/2 acceleration times time squared. So 0, we're going to go ahead and plug those numbers in. 0 is equal to 50t plus 1/2 times negative 10 times t squared. And so as we go through this, we're going to subtract 50 from both sides. We're going to subtract, 50t from both sides. And so that part goes away, and I get negative 50t is equal to 1/2 times negative 10t squared. Well, 1/2 times negative 10, we'll just do negative 5 t squared. I have a t on both sides, so one of those t's crosses out. So I have negative 50 equals 5t. I'm going to divide both sides by negative 5. That goes away. And so my time comes out to be negative 50 divided by negative 5. Negative 50 divided by 50 divided by 5, is 10 seconds. So that's how we would find the time. Now, for this one, it's all in the y direction because we were throwing our object straight up and straight down. Here is going to be different for example 2 because we have a horizontally projected object. So with this one, we have the car that drives off of a cliff and lands a distance away. We wanted to know the initial speed of the car. If we look at this idea, right, the car and the cliff, the car is going to drive off the cliff with some initial velocity. This initial velocity is all in the horizontal direction. So the moment we get into something having horizontal initial velocity and then taking that parabolic path to the ground, we have to take all of our information and split it up into x stuff and y stuff. If you don't do this, you're done. You're going to completely miss the problem. There is no way to solve this problem without splitting things into the x and into the y. And because we're doing that, we know some things automatically. We know automatically that the acceleration in the x direction is 0, and that the acceleration in the y direction is 10 meters per second squared down. Every single time. Automatically we know that. We also know that because all of the velocity is in the x horizontally, the initial velocity in the y direction is 0 meters per second. That is a guaranteed thing that we know every single time. So these three pieces we always know. Now, it's telling me that the cliff is 5 meters tall. If we do that, if we look at that 5 meters, that's a displacement in the y direction. That's telling me how far we move on that y or on that vertical axis. So that piece of information is my delta y. My delta y is 5 meters and it's down, right? We start off at the top and we go down the delta y in 5 meters. And then it lands a horizontal distance of 15 meters away. So this distance is 15 meters. Well, it's a distance because it's in meters and it tells us it's a distance. And because it's in the x direction, that's how far we move in the x. Our delta x is 15 meters. And what we want to know is the initial speed of the car. Well, the initial speed of the car is all in the horizontal direction. We want that initial speed. So given the information that we have, and the fact that the acceleration is 0, the only equation that we can use here is delta x is v initial times time plus 1/2 acceleration times time squared. Since the acceleration is 0, that's going away. And I've got delta x equals v initial times time. Well, I have the delta x. I'm looking for the v initial. What I don't quite have is time. I'm going to get the time from the y direction. So here in the y direction, one of my unknowns becomes time. So looking at these four variables, the equation I'm going to use in the y direction is delta y equals v initial times time plus 1/2 at squared. And the only things I'm going to use are things that appear in the y direction. I'm not going to use any of the x direction stuff for this problem. So we're going to plug in our numbers. 5 is equal to 0 times time plus 1/2 times 10 times time squared. So that 0 times time part goes away, and I get 5 is equal to 5t squared. So if we divide both sides by 5, t squared is equal to 1, and if we square root both sides, the time is equal to 1 second. So I can use that over here now that I've found it, and so that gives me the delta x, 15 meters, is equal to the initial velocity, which we don't know, which we're looking for, times 1 second. We'll divide both sides by 1 second, and we get that the initial velocity comes out to be 15 meters per second. Again, that's using the x and y columns and breaking our information up into x and y stuff. This is the only way you can solve these problems. These are the steps that you take. So we have one more example that's like that. We have a cannon firing a projectile with an initial horizontal speed. Again, when we look at this, we have a cannon. There we go. And it's going to fire initially in the horizontal direction, right? That's all in the x direction. So we have to do what we did before, look at our x and our y columns. And automatically when we're looking at x information and y information, the acceleration in the x direction is 0 meters per second squared, and the acceleration in the y direction is 10 meters per second squared down. This is, again, automatic information that you know every single time. We have to put it into x and y columns because we have two different kinds of motion. And since that initial velocity is all in the x direction, what we're going to do is say that the initial velocity in the y direction is 0 because this initial velocity is all in the x direction. That's the automatic information we have. From the problem, as we look through it, it has an initial horizontal speed of 200 meters per second. That's this initial velocity up here. That's in the x direction. It's 200 meters per second. And it's doing it from a height of 45 meters. That means the cliff, the place where it's at, I guess, is 45 meters tall. So that means the cannonball goes down 45 meters. That's a displacement in the y direction. 45 meters down, 10 meters per second squared down. They're in the same direction. That's in the y. And I want to know, how far away does the projectile land? That is the delta x that we don't know. So my unknown is delta x. And just like we did before, because the acceleration is 0, the only equation that we've got is delta x is v initial times time plus 1/2 acceleration times time squared. The acceleration goes away, and so that delta x is going to be the initial velocity times the time. We're going to find time with our y information. So for all that y information, time is an unknown. All of this stuff is in the equation delta y is equal to v initial times time plus 1/2 acceleration times time squared. So with all the information we have, we can plug it in, right? 45 is equal to 0 times time plus 1/2 times 10 times time squared. So 45 is equal to, the 0 times time goes away. We've got 5t squared. Divide both sides by 5. So the 5's go away. 45 divided by 5 is 9. So 9 equals t squared. If I want to solve for t, square root both sides. So 3 is equal to t. That's my time. Put it back in over here. So for this problem, delta x is going to be the initial velocity, 200 meters per second. Again, we have to use our x information here, times the time of 3 seconds. So our delta x comes out to be 600 meters.